of 62.83 radians per second. Okay, we multiply this out, and we get 2 times 62.83 equals 126 meters per second. Okay, now notice the meters per second. Now you may say, well, what about the radians? The radians actually, it's kind of like revolution. The radians, when we're in a calculation, don't, from a unit point of view, they don't really, when you do this kind of calculation, they don't really show up. We can really just say 1 over second, but we'll say radians per second. But from a unit point of view, this becomes meters per second. So this is the actual velocity, 126 meters per second. So in other words, when this rock is spinning around, if we were to cut the string at this point, this rock would fly out in a straight line at 126 meters per second. Okay? What we want to do now is, again, this is not in the book. In fact, none of this is in the book, what I've just presented, at least not in Chapter 7. But this is important information to be able to understand the concepts behind this chapter. And in my opinion, the author should have gone over this. But he didn't, so I will. Okay, now what we're going to do is, if you look on page, what is it here? 222, we see the equation for acceleration. Centripetal, what's called centripetal acceleration, centripetal acceleration equal v squared over r. What we want to do is we are going to actually derive that, even though the author doesn't, and go to page 218. And the author does have a really good diagram here. And okay. We have a rock. Say we have a rock that's spinning around a certain radius. Okay. Now, what we're going to look at is what kind of acceleration does this rock have. When you're spinning around this rock, we know what the tangential velocity is. We just calculated what the tangential velocity is. Remember, the tangential velocity equals r times omega, the angular frequency, where omega is fundamentally, it's a change in theta over the change in time, okay, of the number of radians per second. That's angular frequency. Now let's look at the acceleration that this rock must be experiencing when it's flying around. Now we know from chapter 1 and chapter 1 and chapter 2 and chapter 4 that acceleration is a change in velocity over a change in time. And we know that this is a vector quantity. All right? You, of course, remember that. Okay. If we're spinning this rock around at a constant rate, the tangential velocity, at least the numerical value of the tangential velocity, is the same. Like the last time we calculated for 2 meters at 10 revolutions per second, the tangential velocity was about 126 meters per second. Suppose we keep spinning it at a constant rate, that tangential velocity would not change. But what does change? What does change is the direction. At any given moment, this is changing direction, right? It's spinning around. Remember, this is a vector quantity. The vector quantity has to do with the magnitude, but also direction. So, is when this, in order to keep this mass spinning around, this rock spinning around, we have a certain mass here, say it's a rock, we need to be supplying what's called a centripetal acceleration. The rock has to be experiencing a centripetal acceleration, and then centripetal acceleration is given by, it's a vector quantity, that's a change in velocity divided by the change in time, and it's the change in velocity. But we know that the magnitude isn't changing, so what's changing? The direction. Well, how do we deal with that mathematically? What the author says is that actually, if you look on page 222, the author just gives the formula v squared over r. And that is the numerical value of the centripetal acceleration, v squared over r. But how do you get it? Turns out it's not so easy. But we're going to derive it. Normally, this is done in college physics, and it really, if it's done, let's say this, if it's done the way it normally is you use calculus. We're not going to use calculus, but we're actually going to point in the direction of calculus, but we're still going to derive it. And this is how we're going to do it. Okay? Suppose I look at this, and I just look at a small arc. That is, at this point, point A, for a split second, it goes from A to B through a small angle, delta theta, and we know that the arc length, like before, is delta S. Okay? And it does that in delta t, time. Okay? So I'm going to erase, what I'm going to do is we're going to focus on just this portion of the arc, and we're going to expand it. Okay, so imagine just this portion here. Now I'm going to erase this, but I'm just going to draw it again, but an expanded version of it. Okay? Just bear with me. Okay, I'm going to draw the arc from, let's see, from here to here. Here's R. This is the center. And at point A, it's here, and then at point B, it's over here. Okay, so the arc is coming through like this. So that's just a small arc, and here is the angle. Here's the delta theta. And from here to here is, that length of arc is delta S. Okay? Now, what I'm going to do is draw what the velocity is at this point A, and then at point B. Okay, at point A, the velocity is tangent. Okay, we'll call it VA. That is, it's the velocity right when the rock is in that A position, and the velocity right here in the B position is again tangential to that. That is, and then we'll write that VB. I hope you can see this. Okay, so remember this is tangent, it's tangential velocity, so this is a right angle, and this is a right angle. Okay, so what we have, and this is a radius from out here. What we have is that these are two vector quantities. That's a vector, and this is a vector. Okay, and we have let's look at this again. Remember, S, we're going to start from the basics. S, arc length equals R times theta. Now if we just change theta by little delta theta, then we change just this little delta theta right here, then we change the arc length by just a small little delta S, arc length. and this is how they're related. Now I'm going to divide both sides, again, by delta t. So this gives us our tangential velocity, as we know. Tangential velocity is r times this. Okay. Now let's look at acceleration. The acceleration, and again, this is a vector quantity, is the change in velocity over the change in time. That's the definition of acceleration. What I'm going to do is I'm going to invoke what we call in calculus, we call it the chain rule. You may not know this, but I'm going to introduce it early. It goes like this. Since we're dividing, well, the chain rule goes like this. I can say I'm going to divide by delta theta, and then I'm going to come out here and say delta theta divided by delta t. We're invoking what's called the chain rule. It's really a calculus idea. The idea is this. Notice that if I say delta v divided by delta theta, but I multiply by delta theta and divide by delta t, notice that the delta thetas cancel out, as they have to, and just give us delta v over delta t. Okay, so I can do this. All I'm doing is I'm introducing a variable, I'm dividing by that variable, and then I'm multiplying by that variable, but the overall equation hasn't been changed. Okay, this is the idea behind the chain rule. Now, why do we do this? Because it gets us where we want to go. That's why. It's a little bit of a mathematical trick, but there's a good reason to do it. So I'm going to come in here, and I'm going to divide by delta theta, and then I'm going to multiply by delta theta, right here. Now, immediately, what can we see? When we do this, immediately the second term right here, you'll recognize this as this. This is omega. So this term is nothing more than angular frequency. It's the number of radians per second. Okay? So that's actually easy to understand. Now, this first term, however, is a little bit harder to understand. So what we're going to do is we're going to look at this term right here. Okay, I'm going to, well, I'll draw it. I think you can see this down here. I'll draw it right down here. To explore this first term, what we have to do is we have to look at these velocities. I'm going to take these velocities, these are vector quantities, and I'm going to redraw them down here. Okay, let's see if I can draw this about right. Here's V sub A, okay, and then VB is slightly tilted from it, and I'm going to bring these two, I'm going to put them, remember the vector quantity here's the head and the tail. The head is going in this direction. I'm going to bring these two together. So I'm going to slide this quantity down to this one. I'm going to slide this vector quantity down to this, just for diagrammatic purposes. Okay, here's VA, and then here's VB. They're the exact same length, but one's tilted relative to the other. It has to be because this angle is tilted. Okay, and what I'm going to say is that actually there's VB, well, let me say this. From a vector point of view, I can say, I can take the A vector and I can add to that what I'm going to say is this little vector right here, okay? I'm going to call that quantity simply delta V, and that is equal to VB. Okay, so I'm going to redraw this a little bit better over here, and it goes like this. This is a small diagram. I'm just going to erase this here. What we really have is that at one moment in time, the rock has a velocity at VA, that's the tangential velocity, VA. Okay, and then at another moment in time, it has a velocity VB. So there must have been some kind of, we'll call it delta V term, where from a vector point of view, the A, VA, plus some kind of little delta V equals VB from a purely a vector point of view. Notice that the size of this is equal to the size of this, numerically, okay, but the angle has changed. Now what is this angle? This angle is nothing more than delta theta. Okay, we know that from geometry. I should have, remember here was delta VA, and at another moment in time we had VB, and we spun this radius through delta theta. So that means that from geometry you should be able to figure out that if we spin the radius through delta theta, that the velocity term also spins through delta theta. Okay. Are you with me? I hope so. Now what we're going to do is I'm going to erase this. Now we're going to look at this right here, and we're going to use the equation S equal R theta, and we're going to apply it to this situation here. Okay? This is a little bit hard to understand, but I think you can see it. This is VA, this is VB, and remember, numerically, VA is equal to VB, and I'll put numerically, the absolute value. The size of this is the same as size of this, only the angle has changed. Okay? So we can go ahead and when this delta theta is quite small, we have delta S equals R delta theta. This length right here, okay, I'm going to say is delta V equals, the length of this, delta V, is R. Now the radius in this case is simply the velocity. This is it's the numerical value of the velocity, V, times delta theta. Okay? So, what do we have? If we're now I'm going to simply divide by delta theta. So we have delta V over delta theta equals V. Okay? Now let's make sure we know what we're doing. This V here is the numerical value. This is a tangential velocity. Tangential velocity. Delta V here refers to the small incremental velocity that happens every delta theta. Okay? Notice this term. This is exactly what this is. And also notice something else. This is very important. That from a direction point of view, this delta V is directed to the center. What we mean by that is if here's the velocity A at a small angle later, the velocity VB is here. This change in velocity from here to here, this change in velocity, that delta V, where is it directed? It's directed right to the center. And the smaller we make this angle, the smaller we can see that this delta V is a vector that's pointed right to the center. That's very important. So what we say is that this is a vector quantity, and it has a direction to the center. That delta v divided by delta theta is numerically equal to the tangential velocity, and the direction is toward the center. Well, I'll put a little vector quantity over that to indicate that it's directed to the center. So let's come down here. We're going to plug this into here. This term now, remember, acceleration, there's two terms. There is this delta v over delta theta term and this term. This first term we now know is equal to v. It's v, numerically equal to v. This is numerically equal to omega. And the vector quantity is to the center. And I'll do like that. So the acceleration is v times omega. Okay, now what is omega? Remember that I'm just going to, well, I'm going to put over here, remember that v equals r omega. You will remember this, I hope. So therefore, omega is simply v over r, tangential velocity over radius. I'm going to plug this into here. We have v times v over r, which gives us v squared over r. And the direction is to the center. Okay, so at this point we have now derived this equation. And we call this the centripetal acceleration. And it's equal to v squared over r, where v, again, is a tangential velocity, v squared over r. Now notice the units, and where is it directed? It's directed to the center. Notice the units. The units will be meters per second squared, so meter squared per second squared divided by meters, which will, one of these meters will cancel out, which will give us meters per second squared, which that's an acceleration term. So the units are right. It is an acceleration term. So I'm going to erase this now, but this is the book doesn't go over this, but you have enough knowledge to really understand this derivation. So that's why I wanted to go over it. Let's see here. So what this means is that when you have a mass, when you're spinning a mass around a certain radius, it has a certain mass, say it's a rock, that there has to be an acceleration. In order to keep the mass going in a circle, there has to be an acceleration. There has to be an acceleration to the center. And that acceleration to the center is the centripetal acceleration. Centripetal acceleration. And it's equal to v squared over r. The tangential velocity is v, and the acceleration toward the center, going to the center, must be v squared over r. This is what's necessary in order to keep the rock spinning in a circle. If the, okay, now, think of F, let's extend it a little bit more. Think of F equal ma, Newton's second law. If there's an acceleration, there's a mass, there must be some force. So what we say is that the centripetal force is equal to the mass times v squared over r. And this is the very first equation in the book, mv squared over r. So this would be the force, and again, the force is also directed right to the center. Fc, AC, they're both vector quantities, and they're both directed to the center. what this means is, essentially what this means is this. If you're spinning a rock around in a circle, you have a string here, you have to supply a force. And that force is the centripetal force. And that force, if you supply the force, then the acceleration will follow. If you stop supplying the force to keep it in a circle, then if this force becomes zero, suppose you cut the string, that would make the force go to zero. Then if the force goes to zero, then the acceleration goes to zero. And if there's no centripetal acceleration, what happens to the rock? The rock flies out at a tangent. You cut the string, boom, the rock immediately just goes in a tangent and it flies out of a circle. In fact, it flies along a straight line. Why does it fly along a straight line? Because there's Newton's first law. There's no more forces acting on it, well, other than gravity. Let's ignore gravity right now. There's no more forces acting on it, and so it flies in a straight line. In order for this rock to fly in a circle, you have to provide a force to change the direction. And that's what the centripetal force does. It's a force that's always directed to the center. Okay? Well, that's a long-winded explanation of the first about 4 or 5 pages of this chapter. And we have worked through a lot of really we've worked through about the first half of the chapter really, but you can see. In fact, let's just. Well, I won't do. You can do some of these practice problems by yourself, like on page 225, 226, and 227. It's really just working with this equation. If, for instance, if you have a suppose this is a car, and the car is traveling around a circle. The car has a certain mass, then there must be some kind of centripetal force holding the car in a circular motion. And in fact, there is. And if the car is going at a certain speed, you can calculate what that force is. And again, this is a force. When you calculate the centripetal force, it will be in newtons, so many newton. Okay. In the case of a car going around the curve in a circle, what provides the centripetal force? It is, if this is a road, it's the tires. The tires connect with the road, and the friction here, if the car is turning, say we're looking at the end of the car. There's a car. The car is turning this way. It's this friction right here that there has to, as you're turning the wheels, there is a friction motion caused by the car, which provides the necessary centripetal force against the road to keep the car moving in a circle. Okay. Okay, we're not going to work any of the little practices of problems. We're going to go on. And let's go over one thing on page 228 and on page 229. And that's the difference between, and this is somewhat confusing, difference between centripetal force, okay, which we'll call FC, F sub C, centripetal force, which is what we just calculated, mv squared over r, is the force necessary to keep a mass traveling around in a circle. And we're going to compare that to what's called centrifugal force. Okay. In physics, we always deal with centripetal force. Centrifugal force, F-U-G-A-L, centrifugal force, is really, and the book talks about this, but this is really what we might call a fictitious force. Fictitious force, I hope I spelled that right. And this is a force that you feel that throws you to the outside. As an example, if you are suppose you're in a car, I guess is a good idea, is you're in a car and you're going around a tight curve, and here you are sitting here and you're going around this tight curve. What happens, suppose you're in the right-hand side of the car, the passenger side of the car, what do you feel? You feel thrown to the side of the car, all right? And you feel something that throws you to the side of the car, okay? And people say that's the centrifugal force. Centrifugal force. Actually, what you feel is something that's pushing you out, okay?